Okay, thank you for the introduction. And let me just say that it's an honor to be speaking here today with so many people who have been thinking about knotted surfaces for so long. And I'm very grateful to the organizers for the opportunity. So what I'd like to talk about today is a new way of thinking about knotted surfaces in four manifolds that comes from the trisection, adapting the trisection theory of Gay and Kirby to this relative setting, and is sort of a direct analog of the way that classical knots and links in three manifolds are studied via bridge splittings. So there'll be four parts to the talk. First, I'll give a quick overview of trisections before defining bridge trisections, and then I'll talk about two particular instances where the theory seems pretty nice. First, knotted surfaces in the force sphere, and then lastly, the setting of complex curves in complex surfaces. Okay, and I should say that all of my work on bridge trisections is joint with Alex and or Peter Alex Zupan and or Peter Lambert-Cole. Okay. So first, I think it's useful to understand what a trisection of a closed four-manifold is before we start complicating things a little bit. So throughout, I'm going to let X be a smooth, oriented, orientable, connected, closed four-manifold. Okay. So the first definition then is that a trisection, or maybe a G, K1, K2, K3 trisection. So don't be too worried if the notation seems a little unwieldy. It's really not so bad once you see what's going on. And I'm working in sort of the most general case here. So a trisection of X is a decomposition. X equals X1, X2, X3. Was that this? Okay. Which has three properties. So the first property is that each of these pieces is congruent to a boundary connect sum of K sub I S1 cross B3s. So it's a four-dimensional one-handle body. Okay. The second condition is that the pairwise intersections, which I'll call HI, which will be XI intersects XI plus 1, is congruent to a handle body of one lower dimension, namely just a normal three-dimensional handle body. And then lastly, the triple intersection, X1 intersect X2 intersect X3, which is also the boundary of each of the XI, is we'll call sigma. And this is congruent to a surface of genus G. So the standard schematic, which is not so useful for understanding what a trisection, or any properties about a trisection really, but it is useful for keeping track of the notation, is that we have a surface sigma in our four-manifold X, and the surface is sitting in the middle, and it bounds three handle bodies, H1, H2, and H3. And these handle bodies together bound standard pieces X1, X2, and X3. Okay. So that's the basic definition of a trisection of a four-manifold. Any quick questions? So maybe the first remark I'll make, so we'll have some facts, and then we'll have some theorems, and then we'll have some questions and conjectures. Okay, so the first relevant fact is that X is determined by its spine. Which is the union of the handle bodies. Okay, and this is, well, it's really far away now. This is because of Laudenbach-Pointeré, right? The union of any two handle bodies is going to give a connect sum of S1 cross S2s, and this can be capped up uniquely by one of these xi's. Okay, and the upshot of this is that this gives us a diagrammatic theory. Okay, this is what allows us to study four manifolds using trisection diagrams. The second thing I'll say is that I'll say it like this. Xi corresponds, or let's say it like this. If we have complexity G, K1, K2, and K3, then X has a handle decomposition with K1, 1 handles, G minus K2, 2 handles, and K3, 3 handles, plus a 0 handle and a 4 handle. Okay? So in some sense, those X's are corresponding to the indices of the handles. But what's really philosophically interesting about a trisection is you don't really see 2 handles in this description at all. And that's because they're on the same level as 1 handles when you're working with a trisection. So in particular, if you have a trisection, it's possible to extract 6 different handle decompositions in which the roles of the 1, 2, and 3 handles are permuted symmetrically. Okay, and then just 2 more mild observations. The other characteristic of X is 2 plus G minus the sum of the K's. And then lastly, I'll just note that the rank of pi 1 of X is bounded above by the minimum of the Ki's. Okay, so in particular, if some Ki is 0, then X is simply connected. Okay. Any questions so far? Maybe we should look at some examples. So, like I said, the trisections are determined by their spine. And so in order to encode a trisection, all we have to do is draw a picture of the central surface and then just describe the 3 handle body extensions. And a handle body extension of a surface is just encoded by a cut system of curves. So for example, if I want to describe a genus 1 trisection, I just draw 3 curves on the surface. Pairwise, the curves are describing Hegardt splittings of the boundary of the xi, which are these standard manifolds, connect sums of S1 cross S2s. So for example, here, pairwise, the curves give me the Hegardt diagram for S1 cross S2, while here the curves give me pairwise the Hegardt diagram for S3. This also gives pairwise the Hegardt diagram for S3. So K is 0, K is 0. Here, 2 of them give me S3, and 1 of them gives me S1 cross S2. And here, all 3 of them give me S1 cross S2. Okay, so these are 5 nice examples of trisections. Okay. So that's some basic facts, and you should feel free to kind of think about why these might be true. None of these are particularly difficult, and they're good to think about. So along the lines of more difficult things, we have some theorems. Of course, the first is the theorem of Gay and Kirby. That's the classical result from 2012 about trisections, which is that every, I'll say X so that you know it's the right type of manifold. Every X admits a GK trisection for some G bigger than or equal to K bigger than or equal to 0. So I guess two remarks. Well, it's a good theorem. But the first remark is that if all the k's are the same, I'll just write k. So the notation here is that k1 equals k2 equals k3. We call this a balanced trisection, and now the notation's a little simpler. Second remark is that there is a relationship between g and k, and you can think about why that is the case. And then the second result is that any two trisections of x have a common stabilization. So a stabilization is some type of operation that increases the genus of the surface. And if we start with two different trisections of x, we can always make them isotopic after performing this operation some number of times. So we have an existence and a uniqueness statement for trisections of four manifolds. Any questions so far? Okay, we're almost to knotted surfaces, don't worry. All right, so the next result is one by me and Alex, which said, it was a classification result. There is a unique, irreducible genus 2 trisection. Okay, what does irreducible mean? Well, connected sum gives, in the obvious way, gives a totally well-defined operation on trisections. Right, I could take these two genus 1 trisections and I could just tube the surfaces together in the complement of the curves, and I would have a trisection for the connected sum manifold. So it turns out this is the only trisection of genus 2 that is irreducible. Of course, you could sum these together and get some genus 2 ones, but this is the only irreducible one. It belongs to S2 cross S2. So one interesting thing about this result is it uses only three-dimensional techniques. Okay, this uses a special feature of genus 2 Hegardt splittings of the 3-sphere, and a lot of complicated combinatorics. You know, it's evidence of a philosophy that trisections, being an analog with Hegardt splittings, are a way of bringing three-dimensional techniques and theorems into dimension 4. Okay, I think then the last thing I'll mention is a recent result of mine from last year, which says that there exist infinitely many four-manifolds admitting GK trisections. I should have said distinct in here somewhere. Infinitely many distinct four-manifolds admitting GK trisections for each. So now we have to be a little careful. We have to say G greater than or equal to 3 because of that. And we also have to say K between 1 and G minus 2. Okay. And the proof of this is basically to understand how the spinning operation behaves with respect to Hegardt splittings and trisections. So it turns out if you take a Hegardt split 3-manifold and you spin it, you naturally get a trisected 4-manifold. And so you can make some basic arguments using the rank of the fundamental group and certain connect sums of 4-manifolds to realize infinitely many distinct ones for each value.
So if you mean like minimally admitting GK trisections, right?
Yeah, I do. Thank you. Admitting, minimal. Thank you. So minimal in the sense that it's the lowest possible G. Thanks. Yeah, that makes it a little bit more difficult. So one example of this is this guy right here. So this is the spin of RP3. Okay, and it admits this nice 3-1 diagram. And you can almost see what the spin of any lens space looks like. Instead of having these these are 2-1 curves out here. Instead of having 3 2-1 curves, you would have 3 PQ curves. And then you have the spin of the lens space LPQ. So they're all genus 3. In fact, I think there's sort of a nice conjecture here. So genus 3, or at least the type 3-1.
Right, what is the spin of a three-manifold?
So spin of a three-manifold, you can take the three-manifold and cross it with S1 and then serge or out a point cross S1. Or you can take the three-manifold and puncture it and cross with a disk and take the boundary.
So these are true equivalent descriptions.
What?
These are true equivalent descriptions.
Yes. Yeah, exactly. Yeah. It's kind of like crossing with S1, but not really. In particular, it preserves the fundamental group. So that's kind of the important thing.
So this is the same as like puncturing it, crossing it with S1, and then like, okay.
Crossing with D2 and then taking the boundary. Yeah, that's right. So the first interesting case for Heegard splittings is genus 1, where we get all of these lens spaces. So I actually conjecture that every 3-1 trisection belongs to a spun lens space. So I'm sort of claiming, or I'm conjecturing a classification of trisections of genus 3 and k equal 1 of that type. And then I think I'll just finish with a question, which is, is there a G, let's say it like this, is there a G greater than or equal to 0 such that there exist infinitely many distinct X admitting G0 trisections? Okay, so this is irreducible. Or I guess you don't really need to say that since you have infinitely many, but. So this is, I think, the really interesting case. So these things are all simply connected. They can be built without 1 handles and 3 handles and sort of a minimal number of 2 handles. They're really, really quite nice. In particular, for low values of G, they're going to be exotic copies of standard manifolds. Okay, so an irreducible 3-0 trisection would be an exotic manifold with H2 having rank 3. And in general, H2 will have rank G in this case. Okay, so that's what I want to say about four-manifold trisections. Okay, any questions? So basically what I wanted to do, I wanted to tell you how we decompose a four-manifold as a trisection, and I wanted to give you some sort of facts and theorems that set the scene a little bit and let you know kind of what we know about them and stuff. But now what I'm really interested in is taking a knotted surface in that four-manifold and seeing how it interacts with the trisection. Okay, so I guess part 2 is bridge trisections. Yes?
Did you tell us what stabilization is?
No. It's kind of like, it's just like the Heegard.
By 1?
Increases genus, yeah. You can say that it increases genus by 1 and one of the ki's by 1. Or you can do it in a balanced way, so it increases the genus by 3.
When 2 trisections may need arbitrarily many stabilizations to become the same?
We don't know anything about the graphs of stabilizations for manifolds. So for example, a really good question or conjecture is that the four-sphere admits a unique trisection of each genus, just like Waldhausen's theorem in dimension 3. So that's a really good conjecture, and in particular, it would imply, if it were true, these nice Andrews-Curtis groups that are tormented topologists for 30 years, that they're trivial. Okay. Good question. Yeah, I'm not going to really talk about any stabilization operations. All right. Okay, so in order to go from bridge trisections, or trisections to bridge trisections, we need to introduce 2 objects which are a little less familiar. So the main objects there were 3-dimensional handle bodies and 4-dimensional one-handle bodies, which I think most people are pretty familiar with. These are maybe a little bit less familiar. So the first one is a trivial GB tangle. So what this is a pair H tau such that H is a genus G handle body. Right, so H corresponds with the H up there, and tau in H is B boundary parallel properly embedded arcs. Okay, so I have some pictures here of this. Okay, so this would be an example of a trivial 0-3 tangle. So here we have our 3 ball. I'm thinking of sort of the boundary as being down here. And we've got these properly embedded arcs, and if you think about it a little bit, or if you get a sneak peek to here, you can see that these arcs can be pushed into the boundary sphere. Okay, a little bit more complicated. So that's, okay, this is fine. Tangles in the 3 ball are fine. A little bit more complicated is tangles in handle bodies with genus. So for example, here's 2 trivially or boundary parallel arcs embedded in a solid torus. And again, they can sort of be pushed into the boundary. Okay, so that's what I mean by trivial tangle. All right, then the second object is a trivial KC disk tangle. Okay, so a simple way to think about this, actually, maybe not very well illustrative, is a KC disk tangle is what you get if you a trivial disk tangle is what you get if you take a trivial tangle and cross with I. Okay, so let me say that now that you have that in your head, let me say it a little differently. Sorry about the shadows. Seems like there's no way around it. So it's a pair. Now it's a pair XD with X boundary connect sum of S1 cross B3s. So again, X is, oh, that's a little confusing because X is my closed manifold. Well, for a moment, this is an X of the type Xi. And what is D? Well, D is in X, and it's a collection of C boundary parallel disks. Okay, so it's actually a pretty easy exercise to see that this is exactly what you get when you cross a trivial tangle with I. But going up a dimension has some costs because three-dimensional tangles encode a lot of information. So if I take any 2 of them and I glue them together by a diffeomorphism of their boundary, I can recover all knots and links in all 3 manifolds, okay, via generalized bridge splitting. The opposite is true of disk tangles. If I have 2 disk tangles with the same boundary and I glue them together, then I'll necessarily have the double. Any 2 disk tangles with the same boundary are isotopic row boundary. Okay, so this was like maybe first appeared in Chuck Livingston's thesis where he was studying what happens to a Seifert surface for an unlink when you push it into the 4-ball. And then to work in more generality, Alex and I had to apply some sort of 3-manifold topology to work in this more general setting here. So one thing to notice in particular, maybe I'll write this down, is what is the boundary of a trivial disk tangle? So the boundary of a trivial disk tangle XD is, well, it's a connect sum of K S1 cross S2s, and then an unlink, a C component unlink sitting in there. Because the disks are boundary parallel, the boundary link bounds disks in the boundary. So it's an unlink by definition. Okay, so these are the basic objects we need. Any questions about them? Okay, we've made it to the key moment. Okay, so what is a bridge trisection? Oh, I should have said, I guess I'll say it here. So now let's let K inside X be a smooth, closed, embedded surface. Okay, so I assumed that X was orientable and connected, but I'm not assuming that K is orientable nor connected. Okay. So, okay, so let me say this the way I want to say it. We can fix a trisection on X. I didn't give trisections a name yet. Fix a trisection on X. So what can we do? Well, K is in B, C1, C2, C3 bridge position. Bridge trisected position with respect to T if two things happen. Okay, you can probably guess. The pairs xi, di that are given by taking xi and intersecting it with k are kc, ki, ci disk tangles. I'll probably stop saying trivial from now on, but I mean it. So the first thing we want is we want our surface to intersect the four-dimensional pieces in trivial disks. And the second thing we want is that the three-dimensional pieces, which are these pairwise, or I guess they're the intersections of hi with k, are GB, trivial GB tangles. Okay. So that's what it means for K to be in bridge trisected position with respect to the trisection. And let's just write it out. The composition of the pair into three pieces is a, well, let's see. I guess you would call it a G, K1, K2, K3, B, C1, C2, C3 bridge trisection. Okay, but from now on, let's just make it a little bit easier and work with balanced ones. Okay, but I should say, like, you know, when you're talking about this, it's much easier to always be talking about the balanced case, just for expository reasons. But it's really interesting when you have a surface that intersects these pieces with different complexities, right? Because in some sense, that's telling you can turn your head, kind of like flipping a handle diagram upside down, except you have more ways to do it with a trisection, and you change the zero handles in the bands, you know, or you exchange the caps in the bands, and there's really rich stuff going on right here. So philosophically, the unbalanced cases is the place to be. Okay, cool. Any questions? Okay, maybe while I'm here in this place in my head, I'll just say there are sort of two ways to think about trivial tangles diagrammatically. When it's a general handle body, the only thing you can really do is push the arcs onto the boundary and have what's called a shadow diagram. Okay. This is basically just taking a choice of bridge disks for the tangle and flowing it on the boundary and recording the information on the boundary. Note that you can always throw away one of the arcs and you won't lose any information. So I drew all three arcs here, but any two would have sufficed to determine the third. In the case of B3, something a little bit more special happens, which is that we can project onto sort of the vertical disk here, right, whose boundary is on the sphere and goes through infinity. And then what we get is this sort of planar tangle diagram. Okay, so this is going to be, both of these are going to be important in a second. All right, so let's see.
So K is transverse to sigma somehow.
Yes, that's right. So maybe it's determined by this information probably, but the third piece of information is sigma and marked points, which is the boundary of these tangles. Right, it's the boundary you see here for each of the pieces, and they all have the common boundary. Yeah, maybe that's worth saying. I mean, I think it's a consequence, but let's say it right here. So let's call it sigma x, which is x1 d1 intersect x2 D2 intersect x3, D3, which is also the boundary of any hi tau I, is congruent to a marked, a genus G surface with 2B marked points. Yeah, good. That's a good question. Okay.
Can you read off self-intersection and something more about the homology class from the?
Yeah, self-intersection definitely. My guess is that you can probably read off the homology class of the surface fairly easily, but that I can't claim to have worked through the details of that. Yeah. Okay. Let's try to send this up and this down. Any other questions? Okay, we just did all of the hard work. Okay, so now from now on it's going to be much, much better. Hopefully it doesn't feel too technical so far. But how's anything visible up there? Can you see the whole board? Not quite. Okay. All right. So what's next? So what's next is theorem and some facts. Maybe I'll say the theorem out loud while I'm writing. So the theorem from 3 years ago was that Alex and I proved that every knotted surface in S4 can be put in bridge trisected position with respect to the genus 0 trisection of S4. So I guess I didn't draw a picture of the genus 0 trisection of S4, but it just looks like that. Okay, you have the unknotted sphere in S4 bounding three balls, and they sweep through the 4-ball regions. Actually, okay, I should draw the schematic here. Okay, good. This is what I'm supposed to do now. Now I remember. So here's sigma. So this is a slightly better schematic than before. So sigma bounds H1, H2, and H3, which I'm drawing here as sort of half planes. In between the H's are the X's, and then the knotted surface hits the handle bodies in properly embedded arcs. It hits the four-dimensional pieces in trivial disks, which means that when I put on my second pair of arcs, this union had better be an unlink in the three-manifold given by this Haggard thing. And same thing for the third piece, right? So the problem with dimension 4 is whenever you try to build something, at some point you're going to get stuck and you're going to have to ask, can it be capped off? Okay, so do integral surgery on a link. Is that a closed four-manifold? Well, only if the result is a connect sum of S1 cross S2s. So the thing we want to verify here, I guess I can give these things names. That's tau 1. This is tau 2. The thing to verify is that the pairwise unions of the tangles are unknots in this case. I mean, it's just a schematic, but I claim that in the case of S4, this is a very good schematic, right? Because this is the unknotted sphere in S4. These are 3-ball fibers for the sphere, but we're just doing a planar projection, just like I did here with each tangle. So I've done a planar projection of each tangle, and basically all of the information is there. Okay. So, any questions about this schematic? I think understanding this schematic gets you a long way.
So maybe it's theoretical. If you have tau 1 and tau 2, then the disks are determined.
Yes, that's exactly right. Okay, that's very good. Thank you for reminding me. Well, I was going to say it probably, but the reason why trisections are determined by their spine is because we have Laudenbach-Pointerou to cap off those standard pieces. And why do we require that these things be unlinks? Well, it's precisely what I was talking about, where the unlink bounds a unique trivial disk system in the four-manifold. It's a relative version of Laudenbach-Pointerou. That's right. And so that's exactly what you need in order to claim that your bridge trisection is determined by its spine, which lets you have a nice three-dimensional diagrammatic theory for it. Good question, thank you. Okay. So the main theorem here, I'll list this as a few theorems, but this first happened in 2015, and then the more recent improvements were last year. So the strongest statement is that given x and t, so given a closed four-manifold with a trisection, any k can be put in bridge trisected position with respect to the trisection. Okay, so you wiggle it around and then it magically looks like this. Okay. So we have a slightly stronger statement in the case of g equals 0. So if g equals 0, so that means in particular that x is S4 and this looks really good like this. We have this trisection. It's not just them claiming this is S4, but in particular we have the sphere trisection. Any two bridge trisections of a fixed k are stably equivalent. Okay. What is stabilization? Well, it's kind of like if you know what stabilization of a bridge splitting looks like, you kind of know what stabilization looks like here. Basically, what you're going to do is you're going to take some piece of this disk here and you're going to poke it through the sphere, kind of like a finger move or a karate chop or however you want to think of that. So what this theorem says, and again, the stabilization is just, it's a little complicated to explain, so I'm just going to wave my hands at it. But what the theorem says is that if I have a surface in S4 and I have two trisections of it with respect to the genus 0 trisection of S4, then I can perturb them, increasing their bridge number until, and then deperturb them, decreasing their bridge number, and repeating this perturbing and deperturbing until they are isotopic as bridge trisections. Okay, so there's a subtlety here that you should contrast with Dave and Rob's theorem, which is that they proved that two trisections have a common stabilization. We proved that two bridge trisections are stably equivalent. We don't know if that can be improved. It's in the proof, it's necessary in the proof. Essentially to do a band slide, right? You have these moves on banded links, and essentially to do a band slide, you need to stabilize and then perturb and then deperturb and then perturb, and anyway. So this is it's a slightly weaker statement than what you would hope for. But maybe it's optimal, I don't know. Okay, and then lastly, I will say that, phrase it a little differently. Every pair xk admits a, let's put it like this, gk b1 bridge trisection. Okay. So what's the content of this statement? It's that we can assume there is one patch. So this is called one patch. Okay. We can assume there's one patch in each quadrant. What is the cost of this? Well, the cost is that if we go from if we have a bridge trisection that's not one patch, then we need to stabilize the trisection surface and increase the genus of the trisection surface. So it's not true that every surface in S4 admits a one-patch bridge trisection with respect to this surface. You would need to stabilize this. You would need to do the four-dimensional stabilization of the trisection surface to reduce the bridge number and the patch complexity here to what you want. I can say that this is like a meridional stabilization of a bridge splitting of a link in a three-manifold. You tube along one of the bridges. Okay, let me get a few more things on the board, and then we'll explore some examples. Okay. Okay, so some facts is worth noting. The first is that the Euler characteristic of the surface knot is b minus the sum of the c's. So this actually tells you you know, you might think that every surface can be put in one bridge position, where there's only one arc. But that's not actually the case, because if the Euler characteristic is negative, you know, the best you can sort of do is make these one, or what? Don't tell me I actually got it backwards.
It's negative the Euler.
This is negative though? I think every time I've given a talk on this, I've gotten that sign wrong. Okay, did I get the four-manifold one wrong? This one here? They're different. They're backwards. That's my problem. Okay, they're not the same, they're backwards. All right, thanks, Maggie. Okay, and then the next observation is just that K is determined by its spine. Again, right, so the spine is this triple now of trivial tangles. Oh, and then, okay, importantly, so this is an important fact, which is that the Nfold cyclic branch cover, so let's denote this by x sub n of k. So this is the Nfold cyclic branch cover of x along k. So this pair admits a bridge trisection itself. And what type of a bridge trisection does it admit? It admits a bridge trisection of type, let's write it like this. G prime, K prime, BC, where G prime is NG plus N minus 1 times B minus 1, and K prime is NK times plus N minus 1 times C minus 1. So one nice thing about trisections and bridge trisections is they behave really well under branch covering. Okay. And basically the reason for this is because the Nfold branch cover of a trivial tangle is a handle body with a trivial tangle in it. Okay. Any questions?
You don't rely on the certain theorem?
No. So in particular, it's probably time for some examples. Actually, we're not quite ready for this yet. I need to say one more thing. So I think I've said enough for these pictures to make sense to you, maybe. So if you want to just think about these diagrams of surfaces over here while I'm doing this chore. So part 3 is knotted surfaces in S4. Okay, and the idea here is again that we can use this genus 0 trisection of S4. So again, the theorem, going back to the original work, is that every k in S4 can be represented, so this is a diagrammatic theorem, can be represented by a triplane diagram which is unique up to 3 moves. Okay, what are the 3 moves? The first move is interior Reidemeister. The second move is, I'll call bridge sphere braiding. And the third thing I'll call, well, it's this perturbation I was talking about. Perturbation and deperturbation. Okay. So what is a triplane diagram? Well, it's basically this, right? We've got our surface. We know it's determined by its spine, and the spine is a triple of 3 balls with trivial tangles in them. So we project onto a vertical disk in each 3 ball, and we get something that looks exactly like this. This is a little bit difficult to draw over and over again, so we open it up into 3 tangle diagrams. Okay, so a triplane diagram is a triple of trivial tangle diagrams whose pairwise unions are unlinks. Okay, so here we have some examples. And you can verify in each case that the pairwise unions are unlinks. So the unknotted S2, the standard cross cap, and if you want its mirror, or maybe this is the mirror, I don't know. You change this crossing. There's this nice picture for the unknotted torus. And then, one might guess that there's only one knotted 2-sphere. But if there were, it would be the spun trefoil. So that's what a picture of the spun trefoil looks like. Okay, so what are these moves I was saying? Well, interior Reidemeister is pretty obvious. These are just diagrams, so I can move the strands around in the diagram just using Reidemeister moves where I'm fixing the boundary. Bridge sphere braiding is a little bit more interesting. Let's see. The permitted move looks something like this. So I could undo this crossing here if I wanted by applying a braid transposition on the second braid generator, right? But the trick is I have to do it to all 3 pieces. This is like an isotopy of my knotted surface that's supported in a neighborhood of the bridge sphere. And so when I isotope it, those points on the bridge sphere move around. But because this bridge sphere is the common boundary of all 3 tangles, I have to move them all the same way. Okay? And so this would give me a new picture of the same surface. Something like that. Okay, so that's what bridge sphere braiding. And then again, perturbation is just some simple thing where you sort of increase the bridge number.
Jeff, it looks like you've changed the crossing.
I have, but I moved it into a different tangle. Yeah, so in particular, you might have thought what I did is sort of reflected. If I'd simply taken the third piece and the first piece and interchanged them, that would actually be an orientation reversing diffeomorphism of my surface knot. That's why it's hard to keep track of which one of the cross caps this is. But what I will say is you can very easily calculate the self-intersection number for this surface. Okay, so you can check which cross cap it is. The other thing I'll mention is that Alex and I's result that genus 2, that there's a unique irreducible genus 2 trisection automatically gives that there's a unique irreducible 3-bridge trisection, because genus 2 surfaces and 3-bridge tangles are bijectively related by the hyperelliptic involution. Every set of curves on the genus 2 surface can be made invariant under the hyperelliptic involution. So we can prove, we have proved that this is the only irreducible 3-bridge trisection, but the proof has nothing to do with tangles or surfaces or anything. It's very kind of opaque how we actually get to this result. So it would be kind of interesting to have a direct proof of this. And then I should say there's some analog where we can produce lots of different surfaces with unbounded bridge number as we go up. 12 maybe here? Okay. You were right, mod 5, okay. All right, so 12 minutes, that's...
So you said there is a way to compute the self-intersection of the...
Basically, each of these disk systems is giving you a preferred longitude to an unlink, and they're agreeing on each of the tangles. So you follow them around and see how many times you end up linking as you go around. Yeah. In particular, well, I guess this is not, well, if there are no crossings, then the self-intersection number will be 0. But moreover, if there are no crossings, then really what I'm doing is I'm building this thing in the 3-sphere. I mean, I would have no problem filling this in with disks if there wasn't a crossing there. So if you see a diagram with no crossings, it must be an unknotted orientable surface. Okay, so what I want to do is I want to mention two applications, actually, well, of this theory that are nice. The first is that Patricia Kahn and Sashka Kuchikova last year, they actually used bridge trisections to prove something cool about four-manifolds. So they were interested in dihedral coverings, dihedral branch coverings of singular surfaces in S4. They had a family of these that were giving them, that they knew gave them homotopy, so that they could produce homotopy CP2s this way. And they used, well, what they did is they adapted this theory of bridge trisections to the setting of singular surfaces. Basically, you would allow a cone, and you know, if you don't have an unlink, you have a cone. And so they used bridge trisections to show the CP2s were standard. Okay. So this is kind of cool because they said that they wouldn't really have known how to get this result if they weren't using the fact that bridge trisections behave so well under branch coverings. And then the last thing I'll mention here in the setting of S4 is that Adam Saltz has work in progress on a Kovanov theoretic, KH theoretic. You can't solve problems at the board, including spelling. Kovanov theoretic invariant for bridge trisections. Okay, so basically he associates some A infinity algebra to the bridge trisection and can prove some interesting things about it. It's still not clear how much it can detect, but it seems like it has some interesting properties with respect to stabilization and stuff like that. So that's pretty exciting. Okay, so that's what I wanted to say about the setting of knotted surfaces in S4. Maybe I'll actually, yeah, I'm gonna move on. Okay. Are we the top one? No, that's not the right one. Oh, I see how it works. Any questions?
Something about the surface from the tangle?
Sorry, I didn't catch it.
Can you read something from the surface from the tangles?
Can you read something from the surface?
What can you use on the surface to describe the
Well, you mean like the Euler characteristic? You can, so some things that are easy to read off are things like, well, the homeomorphism type of the surface. Oh yeah, I should have said that. You can read off the Euler characteristic somewhere, if you write the formula down, right? And you can calculate pi1 of the complement fairly easily using just like a Verdinger type thing. And you can check, if it's connected or orientable. You can do self-intersection number fairly easily. I don't think calculating the homology class in the more general setting would really be too difficult, but I haven't thought about it yet. Okay, so I have just about 5 minutes left. I'd like to say something about this work with Peter Lambert-Cole. So complex curves in complex surfaces. So I don't know if it's clear, but I'm not really a geometer, I'm more of a topologist. So anything I say about complex structures, what I'm really talking about is I'm just talking about smooth isotopy classes of surfaces where the ambient four-manifold happens to somehow admit a complex structure and the surface I'm looking at happens to be isotopic to something like a complex curve. Okay, so the relevant notion here is that a bridge trisection is called efficient if k equals 0 and c equals 1. Okay, so in particular, it's a G0, B1 bridge trisection for a pair xk. So from what I've said earlier, this implies things like The four-manifold is simply connected. It can be built without one handles and three handles. The complement, this implies the complement of the surface has fundamental group that's cyclic and can be built without, or it can be built with, it has a single cup and a single cap. Okay, so the theorem, which I'll just be able to get out here. So this is joint work with Lambert-Cole, and hopefully I can pull up on the projector some pictures to show you the wonderful pictures he came up with for this. And some of this appeared in a paper Alex and I wrote at the end of last year, and some of it's work in progress that should appear this year. Okay, so let's let x equal CP2 or S2 cross S2. And like I said, let K be smoothly isotopic to a complex curve with respect to some complex structure on one of these manifolds. Then xk admits an efficient bridge trisection. An efficient bridge trisection. Okay, so this is kind of the best you could possibly do, which is a little bit surprising. So for example, if you take CP2 and you take the curve of degree d inside CP2, so again, I'm talking about a smooth embedded curve. So this has some genus according to the adjunction equality and things like that. So this admits a 1, 0, because CP2 admits a 1, 0 trisection. And then this thing is d minus 1, d minus 2, plus 1, 1. There's nothing fancy here, it's just the genus. You're just seeing the genus here. Or not exactly the genus, but like 2g minus 1 or something. And then in S2 cross S2, we have these curves of bidegree AB, okay, corresponding to the homology classes in Z plus Z. And these things admit efficient trisections of type, I guess now it's 2, 0, and this is 2a minus 1, b minus 1, plus 1, 1. Yeah, so it's easier to see here. This is twice the genus plus 1. Okay, so, well, I should show you some pictures of this, I suppose. Oh, I never put the dots in this one. I think there's one here. So these are pictures for bridge trisections of 3 particular surfaces. So this is the degree 1 curve, CP1. This is the quadric, the degree 2 curve. And this is the bidegree curve 3, 1 inside S2 cross S2. And these are all spheres. So that means when C is 1, by an Euler characteristic calculation, B is also 1. So that means these things admit one bridge trisections. And a one bridge trisection can be encoded by a special type of shadow diagram, namely a doubly pointed trisection diagram. So part 5 of my talk is doubly pointed trisection diagrams. And it will be given by Dave Gay. 2 minutes, okay, I'm gonna try to turn on the technology and then I'll be done. So let's see if I can manage that. Kill that, kill that. Are you guys seeing anything?
Yeah.
Okay, enter full screen. Aren't those nice? So these are Peter's pictures. All right, what are these pictures of? Well, if you look at, so there's 6 colors here, by the way. Red, blue, green, pink, light blue, light green. The red, blue, green are the genus 1 trisection of CP2. Okay, I've just taken this picture here, and I've flattened it out on a square with opposite edges identified, and the green curve runs diagonally through. The black things are points. They're the intersections of my knotted surface with the thing, the central surface, and I have all these shadows from my arcs. So these are, respectively, the degree 1 curve, the degree 2 curve, the degree 3 curve, the degree 6 curve in CP2. Okay, so this is the sextic. What's next? This observation that there's lots of hexagons in this picture. Okay, and what can you do with a hexagon? Well, you can actually deperturb a lot. So this is what one deperturbing would look like. You push the pink arc through, and this sort of looks like attaching a band in the blue-green picture, and you do it in each of the colors, and the hexagon goes completely away. And so, for example, the cubic here can be deperturbed until it's a 3-1 bridge trisection, right? So this is a 1 patch, bridge number 3, patch number 1. And the sextic can be maximally deperturbed until, so this is a 36-6 bridge trisection, and it gets reduced down to a 21-1 bridge trisection. I like it better if we draw, you can think about the torus as a hexagon with opposite edges identified. And so these pictures, I think, are particularly nice. Again, the top two are the degree 1, degree 2, degree 3, and degree 6 curves. These have all been maximally destabilized. So these are efficient bridge trisections of these. So the last thing I want to say is, what happens if you take the branched cover over an efficient bridge trisection? Well, since k is 0, there's a formula somewhere. Since k is 0, let's see if this works, and c is 1, k prime will be 0. And c will still be 1. So you'll lift to an efficient bridge trisection of the branch cover and the lift of the knot. And so that's what we're going to do for the sextic. So we take the double branch cover of this diagram, and we get this trisection diagram. So this is now 2 tori with opposite sides of the hexagon identified. And each of the ovals is identified with the corresponding oval here. So like the far right pink oval gets identified with the far right pink oval with a flip along its major axis. So this was described twice last week as a parking garage, or maybe once this week. Was it this week? It's a parking garage. So if you're on the lower level here, which is a torus, and if you drive into one of the ovals, you come out the opposite side of the oval on the second level. Okay, I thought that was pretty good. So this is a 22-0 diagram for K3. Okay. So, and we can do this for lots of complex manifolds by taking branch covers over all these efficient bridge trisected curves we get. So for example, all of the complex hypersurfaces in CP3 admit k equals 0 trisections. And this is kind of cool. This means that these manifolds can be covered with 3 four-balls, right? Which is sort of a weird thing to think about. I mean, that's sort of a very simple way to cover a 4-manifold. And in particular, if you look at some of these complex hypersurfaces, say the degree 5 hypersurface in CP3, it's an exotic copy of a connexum of CP2s and CP2 bars. So that means we have an exotic pair of 4-manifolds admitting trisections of the same complexity. Okay, which is interesting because it's positive evidence for the fact that trisection genus might be additive. Okay, Hagar genus is additive, so you can ask if trisection genus is additive. This is one thing you'd expect to happen if it's not additive is to have exotic pairs with different minimal trisection genus. So that's not happening here. And that's good because if trisection genus is additive, then we have a positive solution for the Poincare conjecture. So I think I'll finish there. Thank you.
I just noticed that your picture of the spun trefoil looks like the one that Seiichi Kamada drew as a 2-braid yesterday. Do you know anything about the connection between those kind of diagrams?
No, but I'm sure there's a very close connection. I haven't looked into that. That's a great project. If anybody wants to sort of look for interactions between the different ways of describing knotted surfaces, of which we have a number now. So yeah, it's a good project.
Other questions? Seeing none, let's thank the speaker once again.
Thank you.